Okay, perfect. So welcome everybody. It's a great pleasure today to have a mini course by Matthias Christandl, who's going to tell us about mathematics of quantum entanglement. So I apologize for technological difficulties. For me, that's the first experience. So I hope it's going to work. But if something, especially people on Zoom, please tell me. Okay, perfect. Right. So,
okay, thank you very much, Anton, for the introduction. And oh, can you see me?
Right now we can see you.
Very good. So this is a two-part mini course. So I'll give a 2-hour lecture today on the mathematics of quantum entanglement, and then at the same time next week as well. And I'll be here both this week and next week. So if you have any questions, I'm on the 7th floor. You're welcome to stop by, and we can discuss some more. All right. So I'll just use the blackboard, and I think I should start on, maybe I start on the left side. And you can test the remote control. I'll start to write something. And if there's something,
you should probably could you switch off the light over the board?
Especially for the people online, if there's something that's difficult to read, please let me know, and I'll try to adjust.
Maybe one more difficulty before we proceeded, maybe Valerian can tell us, right? What I see on my screen here is flipped, so I think that's not ideal.
No, it's only you. We see.
Okay. So I can suffer it. That's perfect.
You can. There is a setting next to the camera. Something on the settings on the camera. You can click something and you see it's not flipped anymore. Anyway.
Okay. But it's no problem. Sorry. Yeah.
Okay, and please let's make it interactive. So you're very welcome to interrupt and ask questions. And I hope you don't mind, even though it's recorded. They will be preserved for eternity as well. All right. So the split from this week and next week is it's both on sort of philosophical aspect and on a mathematical aspect. So this week I will speak about what you may call the standard formalism. So formalism of quantum information theory and a number of applications. And I'm assuming that you don't know quantum information, so I will just kind of like start from scratch. And because I start from scratch, I think that maybe the more interesting aspects are not particularly the mathematical ones, but the conceptual ones. So it's the concepts with the mathematics, and then sort of I hope at the end you see that the deeper questions that are of mathematical nature emerge from there. And I can of course say more about that later, but we need to, I think, have the right setting. So we'll have formalism, and I had a list of things that were given in the abstract. I'm changing them slightly. I want to talk about the topic of randomness. I want to talk about correlation, and communication. And in some sense, to connect it to the title, you may call this sort of like entanglement. So entanglement is sort of like a word for quantum correlation among two parts. So usually that goes under two-party. Entanglement is the one that is connected there. Part 2 next week will be on multi-party entanglement. Okay, multi-party. So correlations among more than 2 parties. And here I'll introduce my favorite mathematical object. That's a tensor, a multi-dimensional array of numbers. If you want to say more like down to earth. And this has applications then in asymptotic. You can do certain asymptotics of them. asymptotics of transformations. We'll talk about that. And maybe sometimes we'll call this a resource theory. And then another aspect is tensor networks. And the mathematical areas in which what I'm going to say play in are in the first part, maybe mostly in the direction of operator algebras, and like at a later point, right? And random matrix or random objects. And on the second part, there's connections more in the, say, condensed metaphysics literature, mathematical physics direction. But also goes into combinatorics and algebraic geometry, or maybe applied algebraic geometry as a tool for these. So these are sort of the mathematical areas that in a certain sense will appear. So, any questions?
It's too early, right?
Too early, but you know, it could be like there's some topic that you have been expecting. And well, okay, so I want to start off really by talking about a computer. Okay, so what is a normal computer in the so-called circuit model? That there is a model of a computer which is a Turing machine, and the circuit model is more sort of like a down-to-earth version of this, which resembles more of when we think of a computer. So a computer typically has a number of input systems, and these input systems here we would call it space. Yeah? It's sort of like the space the machine needs, and then the machine operates for some time. So there's time, and then the machine will take these input systems, and you can think of them as bits, and then do joint operations on a number of them. So for instance, it does an operation on these two together, and then maybe on this one alone, and then it brings another one in here, and this continues, and continues also down here, and at some point, the computation ends, and what you get are the outputs. So there's input, and there's output. So far, so good.
And the boxes, right? There are probably some restrictions on what.
Yes. So typically now, if we talk about the computer in a circuit model, for these boxes, so I'm envisioning bits here as the input, and the boxes are just functions transforming 2 or 3. Actually, it would be good to have one with 3. So the maximum I need is a set of, these are called gates. We need a set of gates. Actually, single gate is enough. It's called Toffoli gate. It's a gate that maps 3 bits to 3 bits, and then you can lay it out in some way. And then there's the theorem, and the theorem it's a call it universality theorem. So so assume you have this fixed gate set. It could be in particular only the Toffoli gate. I will give an example maybe I should give an example now. So the Toffoli gate is this gate. It's usually denoted in this fashion, and the Toffoli gate. What you do is here it's say you have x, y, and z as inputs, and then x and y are coming out as outputs. So these are bits, and then the z is being inverted. I'm writing it now in this way. It's being inverted to not z, right? If x is equal to y is equal to 1. So it's like a doubly controlled. So on 2 wires I have a control, and nothing happens to the z. It just stays z if x or y are 0, and if both of them are 1, it'll be inverted to 1. This is an example of a gate. Another important gate that's maybe easier to yeah, and I can give yeah, let me do another important gate would be the NOT gate. The NOT gate really just like, you know, it just inverts X. Okay, so it just does whenever, if this was 0, it comes out 1, and if it was 1, it comes out 0. And then there is another gate that we'll need later on. These are all special cases of this Toffoli gate. That is the so-called controlled NOT gate. It's just a single controlled X, Y. It's a little easier to write in this way. So X come out here, and here I'm just I do modulo 2 addition of X and Y. So if the first bit is 0, Y just comes out down here. And if this bit here is 1, so so-called control, then this target here will be whatever it was before plus 1, right? And because it's binary addition 2, it will then just swap.
Matthias, there is a question. Johannes, do you want to ask a question?
Yeah, just a little question. Can you write down the name of this first gate so that I can understand it? Toffoli. Okay, thank you.
Some person what's called Toffoli. All right. So what does the theorem say? The theorem says that, you know, if you have such a gate set and you have any function from n bits to n bits, then there exists such a circuit. Maybe I'm just implementing it. Doesn't say anything about how big this circuit is, but that's the statement. So it's a very basic statement in computer science, which sort of tells us that if we have a sufficiently complex computing machine, we actually compute any function with. All right. That was what I wanted to say about classical computer science.
So F is any map, right?
Yeah, it's any function that maps these n bits, like strings of n bits to strings of n bits. And you can always find a layout. So the gate set is fixed. You can always find a layout. And the question, of course, is how well. The question is often how much time do I need to do it? Right? There's sometimes time is the number of gates in total, or now in the way I wrote here time, this is also the name is depth. It's the depth of the circuit. Space and there's depth. Ask now a different question. You can imagine that this is a very sort of large topic then to discuss these. Yes.
Do you have some building blocks for this gate that you can say the rest are already made up of?
I'm sorry?
Do you have some specific building blocks for these gates that is always is combination of those to make them?
Yes, so now, fix. So here I gave you 3 gates. Now if you fix the gate set with these 3 gates, okay, and then you are allowed to use them to make a circuit in any form with these gates. Right?
Just these 3?
Yeah, just these 3, yeah. Actually, these are special cases of the Toffoli.
And you cannot reduce them further. You cannot reduce them further.
No, I think, well, I mean, you can, of course, come up with different gate sets, right, that also have this property. But, I think it was just to illustrate that there is such a theorem. Now you can ask questions like, about the depth of the circuit, about sequences of functions, how long is their circuits, etc. Right?
And what did you write in the box, in the NOT gate?
In the NOT gate, oh, I just wrote NOT. NOT. Sorry. Okay. Very good. Now, if we now want to build a quantum computer, usually it takes, with this type of understanding, its starting point, and then we make a quantum version out of it. Okay? And I will say more about certain mathematical aspects of it, but the basic concepts. Let me see if I want to repeat this or not now. The basic concepts, maybe I use a color, are the same. Basic concepts are the same. There is some kind of input that will change. There is some kind of gate set. This will change, and the question is then the same. So I have, and the question will also change a little bit the statement of universality. And I will explain more in detail now, but here typically the input is now a so-called wave function in quantum mechanics. And instead of like a bit string of n bits, this will be n quantum bits. Say more about that. And there will be also an output of them. And then there will be unitary operations in between. And maybe I'm doing this all now in yellow. We have a theorem that also is the universality theorem. And it's sort of the very basis of what is going on. And I want to do it like that. So any unitary U from now, and these are so qubits will come. Large unitary matrices can be written as a quantum circuit. What does it mean now, the quantum circuit? Obviously, this was a finite gate set, right? I mean, what I gave you below here was a finite gate set. This here is, you know, maybe if we're going to arbitrary long, you know, I can do countable things, right, with it. But obviously, this is like an uncountable set, so I cannot represent. That doesn't work. So what we have to do, I have to make the statement correct. So these are. What are the gate set? So the gate set would be consisting of all single gates. So these are all unitary. All unitary 2x2 matrices. And then we need one additional one, and that you already know, it's this controlled NOT gate. So it's this controlled NOT gate, and if you write it as a 2x2, as a 4x4 matrix, right? So if I write it as a 4x4 matrix, then it does nothing, or it flips the bit. Okay, so these are, and this is typically called NOT gate. Okay, so if you now were to and then you can think of all right. Okay, so if you can assemble, right? So you're given any kind of unitary on this big space, you can then write this unitary as a quantum circuit, so as a sequence of single qubit and 2 qubit gates. This is very nice and in some sense powerful in the quantum version of this here. And I'll maybe before I take questions, I want to on this one, I want to say a few more words about it. Because I wanted to first give you sort of the analog, and maybe certain things were unclear now about what we actually mean about it. See,
this C0 is just linearly extended.
It's just a linearly extended C0 from up here. Absolutely. Yeah. Yes, it's really the same. It's just a linearly extended. But I'll say a little more about it now. Okay, so I want to give you this as a background and at the starting point, and I want to now, I'm a little bit already out of space, out of computing space here. So I will start down here. I want to use a few words about the formalism of quantum mechanics, and then come back, and then I think it becomes clear of how what I just said before, how that was meant. So in any physical system, I need to have a description of my system, and in quantum mechanics, the description of a system is a Hilbert space H. But for us in this field, we usually restrict ourselves to finite dimensional spaces, at least to start with, finite dimensional complex vector spaces, and because Hilbert space has a natural inner product, and right with its natural inner product, complex conjugation, right? So within the natural inner product. So this is a system, and such a system I would associate now to a wire. Okay, so if I have a wire here, I'm thinking about a system here. I'm usually thinking of bits or two-dimensional systems for these wires, but they could also be higher dimensional. Then I have the state of the system. All right, what is the state of the system? Well, the state of the system is usually denoted by psi. It's an element in H, and this element in H is usually assumed to be normalized, so it has norm 1. And then, of course, what we instantly do, because we have restricted ourselves to this finite dimensional space, if we now have an example of d equal 2, right, then you would write psi simply as a vector psi 0 and psi 1. And I have to introduce a bit of slang. And of course, I can write it as psi 0, 1, 0, and decompose it into bases. And the spaces here, you should think of corresponds to the classical state that I'm in one basis or in the other. And usually we denote them as somehow as if it was the bit, right? So we're using a so-called Dirac-Quartet notation, and maybe it's a little bit confusing, maybe it becomes clear later why we're using that notation. So this is really the abbreviation for 1, 0. I just denote it by 0, so this is a vector that's indexed by 0. And the other one is indexed by 1. Okay, so it's as if, you know, I'm sort of like, it's either in the state 0 or it's in the state 1, and you can really always replace this here, this symbol by 1, 0, and then 1. I don't know if this is clear. Is it okay? It's maybe strange notation if you see it for the first time, but once you've gotten used to it, you'll see in a minute why we like it. All right. So what's important now is that is what is time evolution, right? And so if you had a quantum mechanics course, the first thing would come out is Schrödinger equation. But as you saw here, there's in my classical or in my quantum computer, I presented everything as discrete, so we'll not even go there. We'll just define discrete time evolution at, you know, from the outset. We'll have everything discrete, and time evolution is discrete, and it acts by unitaries. Okay, so I want to do this. So it's really a unitary from here to here, and that is one time step in the evolution. And unitary makes sense because we have the product, So we can talk about unitaries there. I have already introduced a couple of unitaries. This matrix series unitary, for instance. I've also told you about these 2x2 matrices that are unitary. It's very good to have an example in mind here. And an example for this is the so-called Hadamard matrix, or the Hadamard unitary. And the Hadamard unitary is just a unitary with 1, 1, 1, minus 1, and then 1 over square root of 2 to make it unitary. So it's just a basis change from from this basis here into the basis 1, 1, 1, minus 1, which typically the vectors are denoted by plus and minus. So the vectors plus, so ket plus is usually 1 over square root of 2, 0 plus 1. So to get you used to our notation. Should start to make sense now. All right, very good. So we got time evolution. We can time evolve our system, right? So we have all the elements. We know what an individual wire means. We know how to evolve things in time. And what we need is still the composition of the system. Composition, or maybe joint systems are combined by tensor product. So that means that if I have 2 wires, right, then the first wire, I call that A, and I call the second wire B, and I have the tensor product of it. All right, and we can do right away. We can do an example here to get us started on the topic. So imagine now I start on my wires with 0, and then you should think of it as being 0 tensor 0. And then we're going to do a Hadamard gate. We're going to do this C0 gate here, and then we're going to look at the output. And then at that step, I kind of like that notation. So the tensor product will of course omit because we have too many of them. So whenever you see this, we'll just omit it, or even worse, I like to write like this. Okay. And then you go to the next step, right? What happens after this time step here, after doing Hadamard on the first one? Well, I really have psi 0, right? On the first one, that is 1 over square root of 2, 0, 0, right, plus 1, 0. With me? Okay, very good. What happens now that we do a C0 gate on this? Okay, sorry for this. Now I'm going to do what happens. The C0 gate, right? These are matrices. So these are linear operations on my basis vector, on the basis, or these are linear operations on a vector space. So if I have this decomposed as linear combination, I can just execute them one by one. The C0 gate does nothing to 0, 0, right? Because at first the control is 0, and here it takes 1, control is 1, and it flips the second one to 1. And
excuse me, just to make the link with the C0 matrix you wrote down there.
Yes.
What's the order of the basis?
Yeah, the order of the basis. Yes. Okay. Very good. Good question. So, so here would be the first. This would be 0, 0, 0, 1, 1, 0, 1, 1. So if the control is in 0. I have the identity matrix, I do nothing. If the control is 1, I flip the bit. It's actually fun, right? So, Nicolas Gisard and other experimental colleagues now here in Geneva excel, of course, in making especially such entangled states and making them in the laboratory. What I think is fun is that you can now do it yourself. And if you want, I can show you how to do it. Either you can sign up for IBM Quantum Experience, or you can make an account with Amazon, and you can take a superconductor qubit chip or an ion trap chip, and you can do this actually just yourself. Sometimes there's a bit of a wait time, but if you send the job and then you can get it back sometimes instantly, and sometimes it takes a few hours or a couple of days because there's queues and then not always online and so on. But so this is really possible. All right. Right. Of course, not quite as pristine as perfect. There are errors and so on. We can talk about it later.
But since you're saying about those machines, how big machines do they have?
There's two parameters to these machines. One is the number of wires, right? And they vary, you know, from 5 to hundreds. But the other, but very important is the quality parameter. Okay, if you tell the machine to do a Hadamard gate, what's the probability with which the Hadamard gate is being executed correctly? And usually you have a few percent error per gate that you go. So if you run 100 gates, you can imagine, and you have a percentage error, then after 100 gates, there's not much left. So this is an interesting topic of error correction, and yeah, if you're interested, we can talk more about it. I'll sort of wipe it a little bit under the rug. Very good. Now I say you can do that, or people can do that, but that was not quite correct, because you or we can of course not understand quantum systems. So after we have taken our quantum bits and executed this here, in order to get a result, we have to perform a measurement. And the universality theorem, and that's when we're coming back to the universality theorem that I wrote down before. The universality theorem I wrote down there is really now without having talked about measurements. Okay? So if you have n unitary, and then you can write this big unitary, it's a statement about how to write these big unitaries as a concatenation of these smaller ones. Right, but now, if we want to execute this, we want to do a measurement, then, well, in quantum mechanics, one of the axioms is measurement. And measurement is conceptually complicated. And the reason I think it's conceptually complicated is that classically, in our classical computer paradigm, we don't actually ever have to deal with it. And the reason, there's also a measurement here, and the measurement in the classical system is just a measurement that reads off the bits. And it's a type of measurement. I could I can read off the bits. That's sort of my measurement of the classical system. In quantum mechanics, you can do different types of measurement. So there's different ways of reading the answer off. And this is what makes it a little complicated. So measurements are given by, and for this course, because it's kind of short, I'm giving you a set of projectors. Okay, it's a set of projectors. So meaning I'm taking them to be projectors, and you know, I'm going to take them to be positive semi-definite. And another thing that we want from our projectors is that they are a resolution of the identity. So if I sum them up, they give the identity. So in particular, this means they're like all mutually orthogonal, and do this. Good. Continue here. So this, and what happens then? Okay, so measurement is given by this, but the measurement should then take the output here at that stage was still an element in my Hilbert space, right? So it takes that output and maps it to something. And what is that something? And that something takes, right, this measurement description, it takes psi and it maps it to psi I. And psi I is now an index. It's not the it's not a complex number. Psi I is now this vector. I apologize for that. Which is the projector applied onto psi, and then right. So, and one has to kind of like say it in a sentence, right? So psi is transformed with probability pi into, so this here is the probability, into a psi I, and psi I is the so-called post-measurement state. And what is it? It is the projector applied on psi, and then divided by the square root of the probability. This way, maybe I should put cats around it, so we're not confused about this. So I'm just going to put cats here. Okay. Have you all heard the term cat before? Yeah. Okay.
In physics, it is common.
Yeah. No, it's okay. But one of the challenges in quantum information is that people come from these different backgrounds. And there was a single computer scientist in the audience, I would bet, have never ever heard of a cat. So, right.
So you should maybe write down what the probability is actually.
I should write down what the probability is, absolutely. So the probability is this. So there's a small pi and a large pi, and this here is a small pi. Sorry, small pi. All right. So this is the post-measurement state. So now,
sorry. So you assume capital PIs are self-adjoint, right? Or this is a
so the cat. You mean these here?
no capital PIs.
The projectors.
Projectors.
Yeah. I'm assuming them to be positive semi-definite, and then everything is good. Okay, finite dimensional, no problems.
Do they need to be rank 1?
No. If they were rank 1, no, they don't have to be rank 1. No, I want to kind of make it general at this point. But I'll give an example. And of course, what is the example? In my example, I'm going to take I'm going to actually take a two-dimensional system. I'm going to take P0, which in my notation is now like this. And I'm always abbreviating it and just writing an X in the middle. And of course, if I write it as a matrix, it looks like this. And then the P1 is, yeah, I should also do it like this. Very good. Okay, so these are two orthogonal projectives and they sum to the identity of I. Okay, so they are a viable measurement according to my definition. And so what happens, and now I can do the first thing, and which we cannot do classically. I think it's kind of cool. So the first thing that you cannot do in any classical system, you start with this. You start with a deterministic system, then you make the Hadamard matrix, right? You know what comes out here. That was the state 0 plus 1, right? And then you make this measurement, and usually it's we like to make it like this, like a little bit of a pointer there. Okay. What happens with 50% probability? Now you can compute the probability, right? You compute the probability, you put the projector into 0 here, right? You compute the probability for this here, and you will see it's a half. So with probability a half, you get the outcome 0, right? Or now if you went to assign a post-measurement state, if you want to record more than that, then the system will be left in the state cat 0. And with 50% probability, you will be left in 1. Okay. Right, this is part of the business model of this Geneva company ID Quantique, to take the system, make this Hadamard on it, and then measure the system, and then you have produced a random number. And according to the laws of quantum mechanics, this is then truly random. Whereas normally what you need to do is some kind of other device that effectively is classical, and somehow you need to then forget some kind of information. So this is sort of random generation. So in some sense, this goes actually beyond what was just here at the same place at the blackboard before, right? It goes beyond this classical computational model. All right. Any questions? And this is, of course, what you can do now in any of these machines. Okay? So if you log on to
some general question. So about implementation, you mentioned some implementation.
yes.
But this is linear algebra, right? Basically.
Yes.
But on the analogous electrical circuit, we can realize linear algebra, right?
Yeah, you can realize linear algebra on a normal.
So does it mean that we can realize at least at this simple level those things?
You can what you can do is you can compute all the probabilities. Okay, so if you have now this linear algebra, as you say, you can now take a classical computer and you can compute the outcome probabilities for all of these things. Okay, regardless of how complicated this is. And you start, and then you compute. You can follow through the circuit and compute all the outcome probabilities. That is possible. So in this sense, you can simulate on a classical computer a quantum.
Yeah, but I don't mean the classical computer. I mean just electrical circuit with impedances, resistances.
Ah, like an analog electrical
yes,
circuit.
Analog, yes.
Well, in the analog electrical circuit, you will
well, even with impedances, I can do complex linear algebra.
That's true. No, I don't know how. So, how do you want to do it? So you want to have then one, but then it holds.
Yeah, so I have some impedances connected in parallel, consecutively. Then I have the rules of calculating the effective impedance.
Yes.
And basically, this boils down to some linear algebra, right? So, and depending on what linear system I want to handle, then probably I can create a scheme, the electrical schema, which implements this linear system.
But what about this measurement story, right? Is it? Can you really?
Yeah, I don't know.
Yeah.
Maybe
So I mean now we have to look at the mathematical formalism, but I think if you normally you will only be able to I mean you could do what you cannot do is somehow this tensor product operation, right? So you can you can build up this circuit, but the space you're operating on will not have the same description. Will not have the same description. But I'm not super up to date now, so maybe we can discuss it later. Exactly of how to write it down.
It is just a technical question. So when there is a good time for a short break, probably.
Yeah, maybe. Let me go a little bit further, but at latest at 4, I would say we make a break. So, because what I kind of want to arrive at. So what you have now seen 2 concepts. One is the concept of a circuit and how to make complicated states, and complicated in the sense we have this word entanglement, which means correlated. Entanglement just means that this here is not a product. in this way. Okay. So if you want the mathematical definition of entanglement, just means it's not a product. And we've seen measurement and randomness appear, and we're just going to combine them now. And something interesting happens when we combine them. So that is really the topic of correlation. So, I'm taking a okay, so we take the measurement we've just defined down here, and we're just going to append it here, right? And then, right, what is the result? And maybe that's what comes out of this measurement. So I want to, right, with a 50% probability, we will discover 0, 0, we'll get outcome 0, 0, and with 50% probability, we'll get outcome 1, 1 of these two here. This is of course a correlated classical bit. Yes, now you have to imagine that you know, Nicolas famous experiments, they involve like putting this at you know, under the Lake of Geneva, right? One in one direction here, and this in the other direction, and having them like spatially by kilometers sent apart. And so with 50% probability, you get 0, 0, 50% you get 1, 1. And you're like, okay, well, that's interesting. It's a non-trivial correlation on the one hand, but on the other hand, it just feels a little bit fake, right? Because I could make a I could just flip a normal coin, right? Or what I could do is I could use one of these devices here to flip a coin. Then I could just write down the result twice on a piece of paper, put it in an envelope, right? The second one, and then just, you know, take a bus, go to the other side of the lake, give it to someone, and then obviously when it's unknown what this bit is, and when both parties, the one here and the one on the other side, open the envelope, then they will discover that it was either 0, 0 or 1, 1. Right? But there was nothing quantum about this. It was just classical randomness, which I had somehow hidden in this envelope and then revealed. So in the sense of my computational model of having a circuit that all was working deterministically, this is still sort of like, you know, my quantum system does something special. But if I have randomness available, either by definition, I just say like, okay, I'm not looking, I have randomness available, I'm forgetting this information, then I can actually simulate such an experiment classically. So with 50% probability, I'm getting 0, 0, and with 50% probability, I'm getting 1, 1. And I think one of the biggest challenges of people working in the field of quantum computation is sort of to explain to people that this is nothing to do, right? This has nothing to do with like entanglement. So what is it then that we can do? Can we do something more at quantum correlations? So these are classical correlations that I can generate with the quantum systems, and they don't feel so strong. I mean, you know. What is now different in quantum mechanics compared to classical is that I have more options for performing this measurement. It's not only that I can do this particular measurement or this particular measurement. I can actually change this measurement and I can use that effectively. And I want to now try to illustrate this to you. And then we take a break. So for illustration purposes, I do something that makes life a little bit easier. Okay, so I'm producing this, but it's sort of like practice for a class. It's a course, right? So instead of at this point, you remember we have the 0, 0 plus 1, 1, and I'm forgetting this overall multiplication sometimes. But I actually want I want a little bit more. I want this guy to be a singlet, right? So I'm using the Pauli X matrix and the Pauli Z matrix here. And then after the Pauli X, right, that flips the second bit to a 1 and this 1 to a 0. And the Z puts a phase, there on the, maybe I want the phase on the first one. Maybe I'll put it up here. Okay. And then what comes out here at that place is 1 over square root of 2, 0, 1 minus 1, 1, 0. Okay, and now I want to choose different types of measurement, and I make the first. First, we notice that if I have a set of 2 projectors, and then what does it amount to in a qubit system? It just amounts to choosing the basis in which to apply this projector 0 and 1, right? That would constitute a different type of measurement. So really, if I'm thinking of a measurement, I could use like a U and a V here, and then I'm applying my standard measurement. Okay? So any kind of measurement that I have, I can put it in this form. All right, so this is a new type of measurement. These are 2 different measurements that I can apply. So I have a choice of measurement given by U and by V. And the interesting thing is the collection of things that happen when I change this here and when I change this. So it's not that I'm fixing U and V, but I'm looking at sort of the entire collection of them. And then I get interesting and strong correlations. And this is sort of what quantum mechanics can do. And I chose now the singlet because then we can do a small example, which is kind of fun. In the example where U is equal to V. Okay, imagine now for the first place, like U and V are just not there, so they are the identity. And then I do the measurement and I had 0, 1, minus 1, 0. Well, instead of having things correlated, I will now either get 0, 1 or 1, 0. So I get them anti-correlated. And now if I take U equal to V, well, this here is the trivial representation, right? If I act with U tensor U on this state here, it stays invariant. So U tensor U on it, if I take them from SU2, right, will actually be the same, will stay the same signal. It's actually kind of surprising. That means that the state at that place hasn't changed. Okay, so regardless of what U and V, what U I choose, as long as I choose the same, the measurement result will always be anti-correlated. Okay, so and this is really a departure from the classical case. And classically, I have only one way of measuring the system and it comes out anti-correlated. Here I have a whole plethora of ways to look at the system, to measure the system, and it will always be anti-correlated. And so that's a departure. It's not now a departure in the sense that I've proven to you that this is stronger than classical.
Do you?
Right?
Yeah, I don't know in what sense, right?
Yeah.
That
Yeah, but in the sense that I haven't shown to you. So in the following sense. So I haven't proven to you this is different in the sense that if you cannot use my statement in order to test me yet, right? So if I'm claiming I'm doing a quantum experiment, right, and the results always come out anti-correlated, I could have just done away with all of this, right? And always produce these anti-correlated zeros and ones. So it's not completely clear, you know, right? The outcome always has to be anti-correlated. I've shown you before how to do anti-correlation, right? I mean 0 and 1, and you're trying to test me, and how can you now test it? And so I think this is sort of like 1935 now. Einstein, Podolsky, Rosen discovered that there is something weird here, okay? But they haven't quite nailed it completely. So it takes up to 1960s that John Bell really said, like, here's the way in which we can see the difference, and that's sort of like Bell inequalities. Okay. Maybe if I take 2 minutes, I'll explain this Bell inequality to you, and then we take a break, because that's natural break. Does it make sense? Yeah, we see something is weird. We can do lots of different measurements. Stuff come also anti-correlated. Clearly, it feels like we can't do this classically. And therefore, you know, there's something new. And now how do we prove this? And the way to prove this is called Bell CHSH, and as part of this year's Nobel Prize, or last year's Nobel Prize in physics, to experimentally demonstrate this. And it basically takes somehow its starting point in this observation. And the idea here is that one has one person here and one person here, and think of them being far apart. And they are being they're being interrogated. Okay, so we usually call this person Alice and this person Bob. And they're being interrogated, so they get a bit as an input. So 0, 1, 0, 1 as an input. And what they have to do is they actually don't have to return, you know, before we were talking about returning always anti-correlated things. They have to do something slightly more complicated. Depending on what the input is, they have to, they win. Okay, so they're kind of like playing a game. They win if certain condition is fulfilled. Okay, so they are being given an input X and an input Y, a bit, and they're supposed to give an output A and an output B. And again, these are bits. And they should have the following property. If X and Y are 0, they should come out different. And if so they should come out different in 3 out of 4 cases, and they should come out the same. They should come out the same in case Y and X be both equal to 1. Okay, that's the game. That's the game Klaus and Shimon came up with, and now you can ask yourself, well, what can I do classically? How can I possibly, how can I win this, right? So, right, so there's 2 players, well, we can play it in principle in this room, right, with 2 of you, and you know, you supply some inputs, and then you have to return an answer without talking to each other, right? So supply separate inputs, and then, so what strategies could you do? Well, you can imagine, you can talk about, it's like a game, right? You can talk about a strategy you're going to implement. And then afterwards, you know, I'm supplying the input. You have to supply the output.
So, sorry, strategy in the sense of the gates. That
no, just think of it now classically. Just completely, you know, we play a game. Okay, we divide you into the left side of the room and the right side of the room. I will supply questions X and Y. And you have to supply answers A and B. Your goal is to win the game. And here's the winning condition. If I supply 0, 0, you should return 2 bits, and the condition you win if the bits that you return are different. Okay, and after I've supplied the information and you return, you cannot communicate in that time. Okay, does it make sense? Do you have a strategy? What can we do? It's a very trivial strategy. Well, I mean, basically each of you gets a bit, and then you can do some computation with the bit, right? There are 4 possible ways of computing on a single bit. Either you return it, or you invert it, or you output always constant 0, or you output always constant 1. These are 4 options. Okay. And then you can do probabilistic mixtures over the strategies, but it's fine the target function is linear. It's fine to do one of these strategies. So you can choose one of these strategies, you choose another of those strategies. And so which one will win 3 out of 4? There's multiple ones that will do. I mean, you could always, I mean, if the left-hand side always supplies a 0, right, and the right-hand side always supplies a 1, regardless of what I input, then you'll win 3 out of 4 times, right? But the 4th you will fail. So probably the quarter you fail. Now you can choose any of the other strategies they're giving you, and always at least one of them will fail. Right? So maximum winning probability for this thing is 75%. Okay? This is called the Bell inequality. So Bell inequality is a fancy word for saying, or the CH-SH inequality is a fancy way of saying that whatever you can do in the system is at most 75%. Okay. And then the question is how to beat it quantum mechanically, and then we take a break. So how do we beat it? Well, I mean, in your previous setup of strategy, if you have a quantum computer or a quantum bit and you have one, then you can, of course, use to set up an entangled state between you. What are you going to do? You're, of course, going to take the singlet state I presented to you before. Okay, what else to do? It's already on the board. You're going to set it up. And then when the input comes, you're going to perform a specific measurement on it. And you don't know what the outcome is. It's not deterministic as it was before. But the measurement setting that you are choosing, of course, should depend on X and Y. So you're going to choose some U that depends on X. The others use some B that will depend on Y. And now we have to kind of manufacture it in some way that we're going to beat the 75%. So in some sense, we're going to spread the probability. We're going to try to increase the probability here and of all of them a little bit. Okay, so basically we're going to increase all of them to the same value. So we kind of like make quantum mechanics and make it a little more symmetric. And it's actually very nice and easy to see what it is. So we're going to draw a circle. Okay, and you can think of the measurement as measurement directions. Okay, so this one here corresponds to the 0 vector, the top here. Okay, so this one indicates the indicates basically that you do the identity matrix here. And now I have to look it up how to adjust them. Okay, you will see what happens. So we're going to do 4. You have to choose 4 measurements, right? 2 for Alice and 2 for Bob. And Alice is going to do the X = 1 measurement. If input is 1, she does nothing. If Bob receives 0, he's going to rotate. This rotation here up to here, that's the Hadamard rotation. So this is the state that is 0 + 1. Okay, so that corresponds to applying the Hadamard. Alice is going to do that if X is equal to 0, and Bob is going to, if Y is equal to 0, he's basically going to do a square root of Hadamard. Okay. And this state here corresponds to cos phi theta, and phi is then 45 degrees. 0 plus, sine phi half 1. And then here you can see it's just a Hadamard more than that. So what you see is, and what we have discovered up here was that if they were to do the same ones, they would come out anti-correlated, right? So if Alice is going to do X = 1 and Bob is Y = 0, they're damn close, fairly close. So actually with 85% probability, they will be, sorry, which one is it? Y equals 1 and here, Y equals 0. So with 85% probability, they will actually hit this, right? So it's a little bit worse than if they had done the same ones. But you see that the angle between these two is the same for Y equals 0, X equals 0. And it's the same for these two. So in all of these three cases, they achieve these 85%. But then X equal 1 and Y equal 1, they're really far away. And if this one was down here, then it would actually be correlated. So they're actually at 85% of satisfying this here with correlation. So these others are basically close, and this is really far away, and therefore you get it. And this way you average out, and 85% is really just this number squared here, which is the probability of having that overlap. And that this way you beat the 75, and then yeah, this way you can now you can do an experiment, and that gives you the Nobel Prize if you've done it earlier.
Is it the optimum 85?
Yes, it's optimal, and it's known as Tserelsen's bound. Tserelsen's bound. And then you can of course ask, can you do better? Are there other games? Okay, so now this is now a whole research field, and you see that it has to do with operators you apply on both sides. And actually, this is sort of the starting point for the resolution of this con-embedding problem in operator algebras that was done by continuing this framework. And that is sort of like the breakthrough from a few years ago. Yeah.
Okay, is it a good point for a break? Okay, I suggest let's have a break of 10 minutes.
Yeah, very good.
All right, so we are all set. Welcome back, and we continue. So I had, maybe I can make it more precise. So I had that question about the last passage. So about this 85% story, and the question was, maybe you can, instead kind of to complement the drawing, maybe you can say what was the operators U and V.
Yes. And I think I will just do the calculation, and then we see what it is. So the take my and then maybe we just compute the 85%, right? So I'm just is it okay if I put it up here, right? So we have to we have these operators U0, U1, V0, and V1. And
since you said that it's okay, the best is not to run between the two boards.
Okay.
Sorry to say.
It's okay. It's okay. Okay. So the U1 will just be the identity operator. The U0 will be the Hadamard. Okay. The V0 will be square root of the Hadamard. And the square root of the Hadamard, it did.
Sorry, Hadamard, is it rotation by 45 degrees or?
Well, no, Hadamard is, if you think of it in the blob sphere, the rotation in the Poincare sphere by 90 degrees. Mm-hmm. But of course, it's the SU2 double cover. Mm-hmm. So therefore, somehow, yeah, the angle is kind of halved. Mm-hmm.
Just a remark, it is also two-dimensional Fourier transform, discrete Fourier transform.
Yeah, it's also the two-dimensional Fourier transform, absolutely. Yes, it's also two-dimensional Fourier transform. But we don't use more properties of the Fourier transform. Well, okay, yeah, okay. I'm just wondering how it would generalize. There's somewhat too many accidents in two-dimensional stuff. So what are the numbers here? I did compute them just before. So we're number 10. find them. I think, well, okay, so what we need here, this is, and then you can work out the rest, right? So I think this is what is supposed to happen. And then this one here is just Hadamard on top of that. Okay? So these are the four operators. And now we want to compute the probability. So let's compute the probability that the result is anti-correlated. Oh, sorry. So let's compute that. And what is it? It is well, okay, so I'm writing it down like this now. So what's the probability of measuring, right? So I start with the singlet. I'm writing it down the formulas in my head before. I'm starting in the singlet, and then I want to measure if I'm in the, if I have a 0 and a 1, and then I want to rotate this measurement. So maybe a better way would be to write like ux p0, right? ux dagger tensor vy p1 vy dagger. Okay. This will be one way of thinking about it. Another way of maybe I should put it. I'm sorry, I put this now. Put the daggers on the left-hand side. And a better way of now writing this, a shorter way, is just to take here the singlet and writing it out, 0, 1 minus 1, 0, divided by square root of 2. Then, like I wrote it down in the circuit model before, that I'm applying yx and vy to it. And then I am measuring if it's in the 0, 1 state. And then I'm looking at the amplitude squared, right? So this is the probability. And then you can check that it's the same as above there. And then the first thing that you should notice is that now in these three cases, in the three cases, so all the cases where not excluding the case y equals 1, x equal 1, the offset of the 2 here is only a square root of a Hadamard. Right? So let me, we could also do it one by one. Maybe I will just do it for one calculation for the calculation x1. So we'll just do the example where x is 1 and y is equal to 0. In this case, I have 0, 1. And then here I have identity. And here for the y equals 0, I have this square root of the Hadamard, right? And then I have here 0, 1 minus 1, 0. Okay. So now if you have any of the other combinations, then it would have here, say, a Hadamard, and here it would be a Hadamard square root, so Hadamard on top. And those would annihilate again with the singlet from just as before. Right. So therefore, the cases is very easy to analyze, and therefore the numbers are all the same. Okay, so now I'm bringing out the square root of a half squared. That gives me a half times here. And now, but this inner product, instead of doing the Hadamard now on this side, I'm doing the Hadamard on this side, right? I'm pulling the square root of Hadamard over to this one. But you already know that the square root of Hadamard only changes the angle from here to here. So so what will happen is that I have here a 0, and then here I have cos phi half 1 plus sine phi half 0. Right? So it's like this applied onto this factor. And then I just have here my singlet, 0, 1, minus 1, 0. Absolute value squared. Is it okay to that point? Yeah. Now, the here you see it had 0 here, will have vanishing in a product with a 1 here with the second component. So I have only 0 that goes together with this one. But on the second side, I have 1 here. So it is really just 0, 1 goes with 0, 1. And then I just have that amplitude squared. So this is half times cos phi squared. So this is a half times, and now there's this famous number. It's a half 1 plus 1 over square root of 2. And that is the 85% probability. And now it says a half in addition. And the probability half is because probability half I get outcome 0, 1, and probability half I get outcome 1, 0, right? At the other component. So the outcomes, if it's 0, 1 or 1, 0, is random. And then I have a probability of 85% of reaching either of the two cases.
But then if you have other case of y1 and it's 0,
yeah,
then,
so
then 0 and 1 will switch.
Yeah, so okay, so I was arguing that sort of like this is already covering 3 of the 4 cases, right? So if I now put, so that was covering the case, this one with this one, right? Now if I go with this one and this one, you see that they have a square root of h in common. That one I again put on the other side, and then I have the same calculation from here. And if I have, right, and if I have this one and this one, no, if I have, my God, yeah, this one and this.
No, you 0 and 0.
Sorry, yeah, if I have, watch, this one, the first one, these two, right? If I have these two, they have an h in common that goes out. And then I'm left with, I'm left with the most extreme ones, right? Which is this one and this one, the 1, 1 case. And then, well, I mean, you can do the calculation again.
That one you cannot have any h to the side. When you have 1, u1 and v1, this is different from the first 3 cases. Yeah,
yeah. Well, I mean, it's different and not, right? So if I now take this one and this one here, then what I would do is the first thing I always notice is that this one flips. This then one of them I can interpret it as first flips a bit, right? So then if I'm taking this and this one, then I would take the Hadamard. Well, I would basically write this here. I guess I would write this here as I mean, I don't know if this is not correct, but I think I would write it as a z square root Hadamard. Sorry, x as an x square root Hadamard, and the x is the bit flip. Right, so Hadamard square, I think gives an x. It's a bit flip. No, it's all taped, but it basically I think it will now flip the 0 to a 1 on the other side.
The formula doesn't look correct. It's square root fh minus to the power minus 1, right? Otherwise, h to the power 3 half cannot be equal to h to the power 5 half, right? You write the h square root of h is equal to square root of h times h squared. That's unlikely, right?
Yeah, okay. We can do it. So we do an h squared.
No, but that doesn't matter, right? But just
I mean, I don't know if they, or maybe you want it the other way around. I think it doesn't. Okay, I don't know. But what is h squared? Can we calculate it?
No, it's x.
Is it x? It's x. Okay, so h squared is x. So somehow, right? So if I now take a, well, if I take a what should I do? Should I take it from the left then?
No, you should invert the square root, right?
Okay, maybe I should write minus square root.
Yeah.
Like this.
Well, it depends what this means, the inverse of the square root, but yeah.
But you see what I mean, that this here is very close to a bit flip. I think this is sort of the point. It's close to a bit flip. And what does the bit flip do? It flips the bit here from anti-correlated to correlated. And then it's the same game, right? Then you're close to being correlated and it gives you the 85%.
I have one more question on the phone, but since I don't understand it, Thomas, do you want to ask it yourself? Thomas?
Yeah, which one? The last one? No, I was a bit lost about this X and Y. Do you have, did your U's and V's depend on X and Y?
Yes. Yeah, so I can, yes, so the measurement I'm choosing depends on the input. So it's now a game. I get an input, like both sides get an input. One side gets the input, Alice gets input X, Bob gets input Y, and they have to respond with an answer A and B. And depending on what their questions are, they will now choose a clever measurement.
I see.
Yeah, and then they return the measurement result from that measurement.
Okay.
Yeah. Okay. Are there any other questions? Yes.
Sorry, h squared is identity.
Oh my God! Really? Oh, that shouldn't be the case.
Because it is trace zero, and any matrix trace zero.
But let's decide. We don't figure out this arithmetic now.
Let's call it homework.
Let's call it homework. Yes. Okay, sorry.
Thank you.
Sorry for the confusion. Okay. Maybe
45 over 2 times 4 is 90. And 90 degrees is not 1.
No, but you can check.
Yeah, maybe I maybe okay, but in any case, it should still be the statement of the probability should still be correct.
Okay.
You agree? It is like trace list. Any trace list to matrix squares to a multiple of identity.
Okay, so I should now do the
1 times 1 plus 1 times minus 1. So the eigenvalue is 0.
Okay, but in any case, what we can do somehow is we can do this calculation, and I will now omit it. It's going to be the homework, and the calculation should come out to be 85%. We do it in this case, but nobody correct. All right. Right. So this was sort of like the end of the first part of the lecture, in some sense, that we now sort of like looked into more detail. I now want to shift gears and come to quantum communication, right? So we had randomness, we had correlation, and now we want to do communication. And
just again, logistically, we have about 25 minutes.
Yeah, it's okay. We'll just sort of like continue the next one. There's different ways you can think about communicating things. You can either send them, right? You know, if you think of now information, you can send them via fiber. If you think of quantum states of light, right? You can send them via fiber. You can transmit them via free space. Or you can also take your quantum information, if you have them on some kind of carrier, and just carry it to the other side. Okay, so there's many different ways in which you can. Typically, when people think about communication, they really think about like sending it or sending it with light or with any other medium that flies, but you could also just carry it over. So concept of communication is kind of broad. I'm going to put a line here because I somehow want to introduce a notation for when something is being communicated. We had the circuit before, quantum circuit, and now if we communicate, Alice has a system. She wants to communicate to Bob, and we just put it like this. So it's kind of like a circuit from here to there, and then somehow the question is what crosses that line, you know. And the natural question in communication is like how much crosses the line, how big is the system that crosses over from here to there. So often somehow one wants to minimize how much is being communicated. So you can call it a transmission cost. And this subject, of course, was started by Claude Shannon in the 1940s. And he has a very nice paper called The Mathematical Theory of Communication. And I'm usually saying it's so like really interesting because he formalized it, right? And his ambition was to abstract from any physical carrier. And but somehow, even though quantum mechanics was around 20 years earlier, the quantum mechanical carriers of information were somehow forgotten. So he only built a mathematical theory of classical information. And maybe if the time span had been longer, he would have done the right thing in some sense. And he was not the only one who forgot. I mean, it took decades, right, till the 1960s, till Alexander Olivo noticed that something was being forgotten. And then he started making this theory of quantum communication that we now very often call quantum Shannon theory, in some sense. So, right. So, so imagine Alice is a system. She wants to communicate with Bob. Then she has to pay for the transmission, right? And usually the way we pay when we transmit something, at least on large scale, then you pay per bit that you transmit. And in the same way, in a quantum realm, you pay per quantum bit that you transmit because it corresponds to the unit that you're going to transmit. Now, we don't really, I mean, usually the setup then starts with having a source. So we envision a source. And I'm giving you now Shannon's setup. Yeah, we envision some kind of source that spits out some information. Then we have an encoder. And then it goes either into a storage or transmission medium. Right. And the question then is, right, how big is that object? And then we have a decoder. And the transmission has been successful if this here is the identity. Right? If this was lossless, sort of a way of thinking about it, right? So if what comes out here at the end, this entire maybe this should be not green, I think. If this entire box here, right, is as if it would have been the identity box. That's the idea. And how is the source modeled? So in Shannon's information theory, a source is modeled as a set of symbols. So we have a system, an alphabet, and I'm denoting this alphabet in the same way as I've done before, from 0 to d-1. And then I have small x's here, and this is a fixed probability distribution. So some fixed probability distribution, and the source spits out a single system, a single time. It's now important to sort of like, we'll later on have sources that are repetitive, doing the same things many times. We'll only do it once now. So the source you can think of as large system, right? it spits out books or something. My source could spit out an entire book if you want. The D would be very large. But so it spits out according to a distribution, one symbol X here. Then we want to encode, we want to store, and we want to decode. Okay, and all what the source specification is given by this probability distribution. And the goal is then to minimize, to make it into a mathematical problem, right? I want to understand what the cost is. Okay, maybe I write it like that. So the cost is, instead of minimize, I write minimum. The minimum of the size of the storage, okay, no size for this, such that there is no error. Okay? Meaning this is equal to the identity. Okay? That the entire thing is again the source. Now it's not that this is equal to identity, such that the source, such that the entire setup is the same as if nothing happened. Okay. And the question is what does this cost? Does it make sense? This is sort of like the most basic question in information theory, and we can just go about solving it because it's easy to solve. So we'll solve it by example. So here is my alphabet. Has actually I'm going to take d equal 3, my alphabet size. So P0 is a half, P1 is P1 is a third, and P2 is a sixth. Okay. And then I can now build what is an encoder. An encoder is such a function that maps input symbols to output symbols. And the question is already, can I compress the source here? Okay, is it possible to make a map to a, is it possible to map the 3 symbols 0, 1, 2 in some way to only 2 symbols, say, such that I can decode again? And we can try, right? We can just try. Here's one way of mapping it. So we map 2 to the other one here, and then we try to build a decoder, and the decoder should spit out 3 things again. But what can the decoder, I mean, without loss of generality, it's again deterministic. Well, so if this was my encoder, right? My encoder mapped symbols 1, 2, and 3 to symbols 0 and 2 to symbols 0 and 1 by combining symbol 2 and 1, mapping them to the same symbol. Of course, trivially, I can't recover this information. I've lost it. So I will make an error. I have now already set it up so the error was pretty minimal. So I made an error, but the error will happen exactly every time when symbol 2 appeared. And there is actually nothing better that we can do. So what we see from this example is that in this particular case, we cannot compress. But now if the probability for P2 was 0, right? If the symbol never appeared, then actually I could compress, right? So then actually my compression would have been successful. And so, that was now proved by example, but the cost, we can just give it immediately a formula. The cost of this here, the minimum storage, is and size of the storage, as I said, right? It's the log of the size of the set of X such that Px is not equal to 0. Okay. And this is commonly known as the Renyi entropy of order 0 of this distribution P. So we have already entropy somehow appearing, even though in some kind of rudimentary form.
But how this relates to classical setting, the way you use the mutual information between the input and output?
But that is when I communicate via a noisy channel. So in some sense, this here is more basic. Okay? This is just the problem of communicating. I have a source, and in some sense, yeah. So the mutual information of input output is it's somehow a generalization of this, where you have noise in the channel and you want to counteract the noise in the channel. Here we just have a noisy source, and we want to compress the noisy source as good as we can. Right. That was classical. Shannon's noiseless coding setup. What happens quantum? Because it's already interesting. It's already non-trivial what happens now. So how is the source described? The natural first, maybe not the most natural, like after an afterthought, but the first. So this is called, yeah, so when Schumacher started this, and so he said, well, okay, so let's take a source and let's model it with a, you know, P, with a probability P phi, it spits out a quantum state psi. Right? Very natural. Instead of having symbols, now I have quantum states. And then I want to build an encoder. And then the rest is just the same, okay? Then I have a storage medium, and then I have a decoder. And now if you think of what I want is minimize the dimension of the space of the storage medium. Now, I haven't really talked about maps that are not unitary, so input and output of all of the maps here, as we have talked about them, were always the same. But a way of thinking about it was if you remember the circuit model, that how can I change the dimension? So imagine I have some big unitary acting here, and for all of the inputs that I'm considering here, I have always the zero factored off at the end, right? If that is the case, then effectively my unitary here reduces the dimension of the space. Okay, so there is a natural way of understanding that. And so what should we do now in this case? And
so sorry, but the unitary can it have such a property? Maybe it's not.
Yes, but it depends on for a specific for a specific set of inputs, right? For a specific set of inputs, it could have that property. Not for all of them, but for a specific set. And because we are here, have only a specific set, so we'll come to that. Now, if now we are in this setup, and now we want to build encoder, storage, decoder such that has this property. Well, we can just kind of like follow the intuition here. Here we couldn't. We had to keep everything where there was something non-trivial happening. All right. So all of the symbols that actually appeared, I had to keep. And it's the same here. And the cost here will be the logarithm, right, of the size of the span of all of the vectors phi such that the p phi is non-zero. Right? And now you can see what my so here my phi's come in, okay? And if say this here is 3 qubits as my example, right, but the span of the phi's is only a 4-dimensional space. Right? But say, right? Say span of the phi with p phi non-zero is 4. Then actually it's possible, right, to build a unitary that maps this into this 4-dimensional space, and then this here could be this would be my encoding map. So it maps it to the smallest space. I store that, right, and then I can decode again by just applying the inverse of it, right? Then in the middle, I have this, like, my storage was only these two qubits. And of course you can put a ceiling here. You know, if I'm kind of wiping my ceilings under the carpet if we don't have 4 and 8, but other. Okay, so this is very natural, and of course, in the same way, I'm raising these ceilings. We can give this again a number, right? We can give it a name, and this we call H0 off. And now here comes an interesting fact: the span of this here is a property, right? This is a property of a matrix, and this is what we call the density matrix that we can associate to the operator. Okay. So we can make a matrix out of our vectors. We obtain this density matrix, and the span of this here is actually the same as. Maybe I should write it. I should make one more step. This is the log of the rank of the operator row, and then this object here, I call H0 of row. If I had a classical source, meaning my symbols are described by orthogonal vectors, then of course my density, so example classical, my density matrix would be diagonal.
And maybe one naive question. But when you were defining the cost, right?
Yes.
You didn't tell us from the very beginning that you would take a log, but then you do take a log.
Yeah, I take a log. Yes.
Yeah, just.
Why do I do it?
Yeah, probably.
Yeah, it's because it's somehow. I mean, I always say, I mean, imagine you were to pay for the number of levels that you have the possibility of sending, right? Then it would be, you know, it's like what you pay naturally. It's like what you pay your, you know, it's at least what in the old days you paid, right? Per, you know, if you have a bad contract and then you fly into Switzerland, it will tell you that you pay, you know, a Swiss franc per megabyte or something. So a megabyte, right, is the log of the number of levels my system has, and that is natural. And it's really how often do I have to do something, right? And it scales linearly with how often I have to send a particle, or how often I have, how many objects I have in my computer. So that's what I take.
Sorry, is it usually log base 2?
Yeah, take base. Yeah, we always take base 2. In information theory, is always log base 2. So it makes most sense.
You transforming to bits, right?
Yeah, we always take log base 2. But sometimes in mathematical manipulations, of course, natural logarithm also appears, but usually it's log base 2. Very good. Okay, so I want to. So now you've sort of seem, and the answer is in some sense a bit trivial, right? It can be. I mean, we can give like non-trivial sources where even this here becomes a little bit non-trivial and figure out what the space and which is encoded and so on. But why did I do all of this? It is because it is now presented in such a way that it would be natural to generalize when we allow for errors in the communication. And this was Shannon's big insight. His really big insight was that you shouldn't try to communicate without error. Right? It's sort of like what you naturally try, right? You should naturally you would try to do that, and it turns out to be you get a better trade-off if you allow errors. So how to allow errors? Maybe we put them in here. We in this paradigm, you want to allow an epsilon error. And I mentioned already that so how do we allow an epsilon error? So if we allow an epsilon error here, the story changes completely. And I'm going back to my original example of the sixth, right? Half, a third, and a sixth. And now, if I'm allowing an error epsilon that is bigger than a sixth, I can just use my original encoder decoder, and it will only make an error epsilon. Right? So I can, if I allow a small error, I actually can do better. I can reject some of the symbols, and it'll be fine. And it's the same, of course, in the quantum case. It's the same in the quantum world. And let me first say a few more words about this case here with error, of how to think about it in a nice way. So I think a nice way is to draw up these histograms. And I make a histogram a little bit more complicated now. So this is sort of like here I put the probability of I, and here I put 0, right? And then maybe I have the second one as, this is now a different example, right? And then the third one is down here, and then one is maybe not appearing at all. Okay, so if my probabilities of the different events are like this, then if I want to think about making an error epsilon, I'm just putting an epsilon bar here somehow. You know, then if there's one event I'm looking for, well, the mass, right? Here now, the mass of this event here was smaller than my epsilon. And in general, maybe it's not so good after all to make this. So in general, I want my, I want the combined probability of the events that I throw out to have, so everything that I mark with pink, I want to have them of being a mass less than epsilon. And then I can go, how do I mathematically formulate now my solution in this particular case? And the solution in this case with error, right? So if I'm allowing epsilon error here, then really what I did, I took my original probability distribution, some of the probabilities I set to 0, and then I look what is the rank of the resulting object, or the log rank. So it's the minimum over the q's that is smaller than p. And then I'm looking of h0 of q. And my q has a condition, namely the mass on the q has to be bigger than 1 minus epsilon. So, right? So I have to, the mass of the q's has to be bigger than 1 minus epsilon. Now that was not so pedagogical. Draw it like that. I'll make a big box around it. Oh, it's a very nice, clean, way of formulating the problem.
Sorry, I got confused. So epsilon is a threshold for each event or for the sum of them?
No, for the sum. Mm-hmm. Epsilon is the total error.
So the drawing was wrong.
Yeah, so that's why I kind of erased my line again. So if you have only one event, it's nice, of course, to look at it like to write it like that. But if you have several events, it's better if you really think of it as the mass of what you took. And so I think time is up. And I just want to give you the formula for the quantum case. And then we can continue discussing there next time. So in the quantum case, it's the cost at epsilon. And then you look for the minimum over all the operators that are smaller than rho. And this now means in the sense of like rho minus sigma being positive semi-definite. And the trace of sigma being bigger than 1 minus epsilon. And then H0 of sigma.
Still non-negative sigma, right?
Yes. Okay. So it's the it's really the analog of that. That is the cost for the communication formula. So you see now a few new concepts creeping in. One is that we have formulated in the language of density operators. And before, in the zero cost level, we could still talk about like the span, and the span doesn't make a reference to the inner product. As soon as we somehow move to arrows, we have to take into account the inner product, and the inner product creeps in through the trace here. Okay. This we could still consider on a subspace, but I really want the mass on that subspace to be big enough. And so that is why we're moving to this density matrix formulas, and we'll do more of it next time. Any questions?
Okay, well, thanks a lot. Any questions or comments here or online? I start with online. So people, do you have some questions or comments?
I just have a little question about how did you call this H0 entropy again?
Oh, it's a Renyi entropy of order 0. Oh, Renyi entropy. It's a Hungarian mathematician. Of course, I don't know all of these decorations. And the Renyi entropies is a family of entropies with a parameter usually called alpha. And if you the parameter varies from 0 to infinity, and the relevant quantity here is the 0th order. It's just another name for the logarithm of the rank, really. But if you then take this parameter somehow to close to 1, right, then you will recover the Shannon entropy, and we'll come to that next time, and so on.
Okay, thanks.
Thank you.
But is there some relation with quantum statistical mechanics in physics based on the density matrix rho?
Yes, yes. I mean, you can, of course, yes, it is. I mean, in that sense, typically in statistical mechanics systems or in quantum statistical systems, right? You describe it also by a density operator, and then you notice that there is somehow some asymptotic equipetition property that allows you to then argue that the mass of the object lies in a small dimensional subspace, or the entropy of that the effective size the system takes, that's the entropy, right? It has a specific size. We haven't really, I wanted to introduce it now like this, and when we go to repetition of the source, right, then we're going to come to the Shannon von Neumann entropy and move there. But I wanted to get the concepts right first. So.
Yeah, but can one develop these things based on this statistical mechanics intuition with partition function, free energy, whatever?
I think if in a statistical, I think the difference in statistical mechanics typically is that you have a Hamiltonian in the background and you want to kind of like play it off some Hamiltonian. Really here, the focus is a little different. It's more on the state of the system that comes out. And on the state that is produced, and somehow then there are no, there are few limitations. So I think maybe what characterizes all of what I said today is that really, in contrast to standard quantum mechanics, is that we never really talk about a Hamiltonian. There is no reference energy. We always like have the system under complete control, and we can apply unitaries, which you of course could think of like switching Hamiltonian on and off for a period of time. But there's no limitations from that point of view. You have like a complete controllable system. This is sort of the, maybe this is a good point of making that. This is really the difference, I think, from going from what people call the first quantum revolution, you know, up to the 1980s to say now quantum computing, quantum information, the second quantum revolution. There somehow is the idea that you can control the system. You can do what you want, and you're not observing only what nature gives you in some sense, but you're manipulating it in the way you want. More like a computer science or an engineering project. Yeah.
Okay. More questions or comments? Maybe you can just say again a couple of words. What's going to happen next time, right? We continue in a week from now.
So so we continue somewhat from now. I want to do the IID limit for here. I want to continue. I want to finish that, and then what I want to do is I want to give you one outlook on how an advanced communication problem looks like. I mean, without proofs, but sort of like it's something called state merging. It's a generalization of this here and going in the direction of the question that came before of like, what about Shannon's formula with mutual information? So I want to give a bit of an outlook there that maybe takes in total 20 minutes and then or half an hour. And then what we're doing is we're moving to multi-party entanglement and then a translation to tensors. And then again, I want to bring you up to a number of interesting research directions. I think this is sort of like generally the theme. I want to show you a number of areas of where then we can go deeper.
Okay, well, thank you very much. Thank the speaker again.